Hey, hello there. So today I'm talking about this question: 410 split array, largest the sum. We have an array consists of non-negative integers and a integer number m. We need to split the array into m non-empty continuous subarrays. So imagine we have the number lined up in a line. We have a knife. We should cut this line of number into m different sections. For each section, we're gonna do a summation to calculate a sum number, so that we end up with m different sum number. We need to take the maximum among this m sum number. So that's one number summary of how we cut the array into m sections. Obviously, we have different ways of cutting that. For every possibilities, we're gonna be able to end up with this maximum among all the subarray sums. We can just compare all the possibilities and actually find the minimum of that. So let's be a little bit concrete by looking at the example. So the example we have is this array of 5 elements: 7, 2, 5, 10, and 8, and m equal to 2. So we have to separate this line of number into two subsections. There are a few ways of doing that. Just gonna try to manually enumerate that to get some feelings about this question. So we got, since that they are continuous, I should not skip element. So we should have 4 different ways of doing that, right? Since the total number of elements is 5, so we should have 4 different ways. So we have one last case, which is a single element 7 in the first and the other 4 elements in the second. So these are the 4 possibilities of splitting the array into m equal to 2 different subarrays. Then for each of the subsections, subarrays, we're going to calculate the sum of the numbers. So this is 9 plus 15 is 24. That is obviously 8. Here it's 9 plus it's 14 and 18. The third split, the number summation is going to be 9 and 23. The last one is 7 and 25. So after we've done the summation, we actually want to take the maximum between these two numbers. So it's 24 and 8, which is 24. The second split, we're going to take the maximum between 14 and 18, which is going to be 18. The third split, we're going to take the maximum between 9 and 23, so the result is 23. The very last possibilities, we're going to take the maximum between 7 and 25, which is going to be 25. So after we got all those 4 different maximum among the subarray sums, we should actually just take a minimum among all those numbers: 24, 18, 23, and 25. So the minimum is obviously 18. So that's if we solve this problem, we should return 18. So that's how we enumerate over all the possibilities for solving this. Notice that we define this, we separate this into 2 subarrays. First the subarray and the second subarray. And we have some kind of a splitting point in between that we split this into two sections. We're gonna try to go a little bit generalize this to not generalize, but slightly more complex. With the same input array, we're gonna try to manually solve at least a few cases in the m equal to 3 situation. So that might give us some hint about how we're gonna be a little bit more formulaic when we think about this question. So again, as similar with this first m equal to 2 case, we're gonna try to have the last subarray fixed, or we can have the first subarray fixed, and looking at the possibilities about the rest of the 2 subarrays. So we're just gonna have the third, change this to third, and then we have to split the first 4 number subarray into actually 2 separate subarrays. So notice that here once we have the last subarray being fixed, the remainder of the problem here, so let's say we split by this number k, element k, by a certain index k, when we just do that. The first half is a problem of a smaller size with a smaller m value, so we need to split the array of 4 elements into two different subarrays. We got a few ways of doing that. I'm just gonna quickly enumerate over the possibilities. That's first one. The second one is 7, 2, 5, and 10. The third one is 7, 2, 5, and 10. Solving this is similar to what we have here. So I'm just gonna do a quick exercise about this. 9 and 15. We do the sum for each subarrays. This is 14 and 10. Among the between the two subarray sum, we take the maximum, 17, 15, and 14. Among these three maximums, we take the minimum, which is 14. And that's the solution to this subproblem of size 4 with m value equal to 2. Then after we solve the first half as the subproblem, we then combine with the fact that the last subarray has a sum of 8. What we need to do then is to take the maximum between 14 and 8 to give us the 14. That's solving when we actually split by this k value here. If we move the k value towards left by 1, we will end up with a different last subarray, which is going to be elements 10 and 8, and a different subproblem with 3 elements, and split that into m equal to 2 cases. Again, very quickly, I don't want to actually. I'm just going to try to calculate the number out. So either 7, 7 or 9, 5. So obviously the minimum is going to be 7. So we're going to take the minimum 7. That's the solution to this 3-element 2-group subproblem, and the sum of the third part was going to be 18. We're going to take the maximum between these two, 7 and 18, which is going to be 18. If we change the splitting point even towards left by 1 more, we will end up with this. So the sum for the latter part is going to be 23, and the solution to the first subproblem is just 7, right? 7, yeah. So that will give us the maximum between 7 and 23. That's going to be 23. So the minimum is this 14 here. So when the problem is of M2, it's not so obvious to realize we can actually using some recurrent subproblem. But with case 3, we see that we can once we fix the one of the array, the remainder problem become the smaller problem of the same type with smaller input and a smaller m value. So let's just formally define this. Since that we are looking at the variable array size, which is the as the way that I'm setting it up here, we are looking at the first arbitrary number of elements, and the m value can also be another variable for this recursive relationship. So that's just going to use 2 variables, I and j. Let's define this to be the solution to this subproblem is going to be the minimum among the maximum sums, subarray sums when splitting array towards this j's location and into I groups. So if we have this function all figured out and we can just use it, then the question is basically asking where we just substitute the ij with the actual number here. Is it called nums? Yeah, nums. So size. So that's what this question is essentially asking. If we implemented this Fij, we just put in m and the size of the array, we should get the answer that we want. So our job is basically to figure out the base case and how the Fij's relationship with something like a Fi minus 1 and some number that's less than j. You know, the bigger size of problem's relationship with the smaller size of problem. So the base case is just if we want to have the I equal number of group into 1, and we take the first j elements. So that's basically doing the accumulative sum. So the base case is easy. Fij is going to be sum of these nums from beginning towards this j location if I is equal to 0. If I is equal to 1. So that's the base case. And then the recursive relationship, we can actually just looking at here. When we're looking at m equal to 3, once we fix this third subarray by splitting in between, using some arbitrary number, the problem becomes the subproblem of from beginning towards that case location and have an m value less than 1 less. So that's going to be something like I minus 1, and instead of to j, we have to doing that for the case location. And the stuff that's after k, we actually just do the sum. So from k to j, you know that among those we take the maximum here, here, here. So we take the maximum between these two quantities, and for all the different k splitting point, we actually take the minimum among these three number. So for k in blah blah blah, we take the minimum among those. So that's the recursive relationship, with all this, we can code up the dynamic programming approach to solve this problem. Just by looking at the formula here, you know that when we're looking at Fij, you think about this as I with the rows and j with the columns. When we do the current row, current I and j, current I row, we only need information from the previous row, so we can just try to code up the 1D version to have the space complexity to be 2 multiplied by the number of rows, number of columns, two physical rows instead of having the entire 2D table. So just by looking at that, we can already see we can do this space optimization. So yeah, so with that, I'm just gonna start to code this question up. So we're gonna have a vector called. So since that we have quite a few numbers, and they actually sum to quite big, so the int is not gonna be able to hold them. We're gonna have something that's doing the accumulative sum. This is the base case for the DP, and it also helps us to calculate all those sums. We can just take the two numbers j and k and looking at those values from the accumulative sum and take the difference. It will be equal to the window sum. And we're gonna have two DP rows. I'm just gonna call this DP and next row DP. So populating this. That could wait. I'm just gonna code the loop first. You know that based on this menu kind of walkthrough, we are working from the m equal to ideally 1 base case, then 2 and 3. So the main loop is gonna looping over the number of groups we need to do. So let's I equal to 1, because base case we can pretty much just populate ourselves without ever going to this loop. And for here we're gonna try to look at the j's location, and for every j's location we actually need to look at a k's position about when we split between the first j element. So there's going to be another nested loop in here. J is less than, let's grab the size of the array, yes. The k will never be greater than the endpoint of this array, and it's it could start it with something that's larger than 0, because for I equal to 1, that's the equivalent to saying that we need one additional than than one group. This could start with something even higher, but that would just add a complexity to the code. So I'm just going to leave this to 0. I will have the initial value to be maximum in this DP rows to suggest that it's not possible. So yeah, let's gonna do this. Yeah, basically we're gonna have a DP that's initially to be the accumulative sum. So each number is basically the sum from the beginning towards that location. That's the initial base case. Then for each new grouping that we are looking at, grouping number that we are looking at, we're gonna initialize this to be vector of lom, and size is n. Initial value is integer maximum. So whenever we be able to find some meaningful number like 7, 17, 15, or 14, we're gonna lower that. So this just gonna pretty much be the same as the relationship. Since that we are inside this for loop to do this formula, we should just take the minimum between the previous calculated Fij with this quantity. So we're gonna do the NDP j is gonna be the minimum between NDP j and the maximum between these two quantities here, which is the previous result towards case location and the sum, window sum. So that's accum j subtracted by accum k. So yeah, so that's the pretty much just putting this formula into this loop here. That it's collecting the k different numbers and doing the minimum. Here I'm just for each new number I'm calculating, I'm taking the previous minimum with this minimum. So this formula here is equivalent to the implementation here. So after that, for each row that I'm dealing with, I'm assigning that back to the the DP is basically the previous row, the NDP is the current row. That's in the end we should just return the DP at m minus 1. That value should be the stuff that we want. So all the left is just to populate the base case. So it starts with the first number in this array, and I'm just gonna looping over the numbers from the first towards the end. So that's the accumulative sum. It's also in our base case, and we also use this to speed up the calculation of the summation of the second part here of 8, 10, 8, 5, 10, 8, those things. Instead of doing the summation, we just look up those numbers and do a arithmetic to get those. And yeah, sorry. And yeah, this is pretty much the recursive relationship putting down here. And we are looking at all the combinations between I and j. For each I and j, we will consider all the possible breakpoints before 0 and j. And we start with 0 so that that's be enabled by we put this into maximum there. Because we're going to take minimum, if there are a meaningful way of doing the split, it's going to drive that maximum number back to some reasonable number. If you don't want this, then you could change the lower bound to doing some arithmetics. So that's pretty much the code, I think. Let me check quickly to see if I got problems. Yeah, let's see. Oh, no. Okay. All right. Yeah, so that's the DP solution to this question. It's not super hard, even it's a hard level question. I guess if you work out this in a manual example in the at least at least a few of the m equal to 3 case, you will feel you will see the clearly see the subproblem here, and the formula is not too bad. The time complexity for this, we have 3 loop here. The 2 inner loop here from 0 to j, the innermost, and j is upper bounded by n, and the middle loop is from 0 to n. So these 2 loops together will be n squared. And this loop here is m. So just gonna comment it on the same line to save a little bit space. So the total time complexity is obviously m multiplied by n squared. And for the space, we are looking at the 2n. So the space is 2n, or 3n actually. Yeah. So that's the time and space analysis. Yeah, so that's the DP solution. It's a okay solution, but it's not why I'm talking about this question today. Because this week I'm doing binary search. The way to think about this question in terms of binary search is that we have a clear search space here. The number that we want to output have a certain search space from 0 to from the maximum number, from the summation of the number, from with the m equal to 1 case, it will be sum of all those numbers. The lower bound is let me comment this. Just copy the signature. Comment out this DP solution and talk about the binary search one. So we got a lower bound, which is the sum of everything, and we have an upper bound, which is going to be the the upper bound is sum of everything. The lower bound is going to be the maximum of all the numbers. That's when we can have each individual number to be of its own group. That's guaranteed that we'll be able to hit this lower bound. That's our lower bound and upper bound. And the reason that we can search for this is that if we can form 18, then that means 18 is the smallest number we can actually do this partition of the continuous, partition the array into continuous chunks. If it's 17, we will not able to do this. If it's 19, we might be able to do it, but 18 is definitely the first one we will be able to do this. So we're just going to do a greedy search to solve this. The reason being that binary search works is let's actually just look at examples. I don't know why I'm hesitating here. So if we look at the 18 or 17, we work on 3 examples, 17, 18 and 19, and we should be able to see the pattern here. If you're looking at the target value that we want to return to be 17, then we look at the array here. We definitely want 7 and 2. That adds up to 9. Since it's smaller than 17, we can definitely put another number in there, and we do want to do that. We want the number to be as large as possible, the window to be as large as possible, the window sum to be as large as possible before it breaks this, because that's gonna be having us to have less number of subarrays. Then we're gonna have set 10, but we couldn't put 8 in there, because if we add 8, it will be larger than the 17 that we are aiming at. Then that leaves us to one last window subarray with the number 8. So the number of split we need to make sure that all the subarrays sum does not exceed, does not greater than 17 is 3. For 18. For 18, basically we're just gonna consolidate the 8 and 10 together. We need 2 splits to make sure that the minimum of the subarray sum is 18. And for 19, we should change this. Sorry, less than or equal to. Then it's clear. Yeah. So if we search for 19, we find that we need 2 splits to have the minimum of the maximum subarray sum to be less than 19. Then that gives us direction. We can try 18. If 18 works, that's the smallest possible. So it's a binary search, and we want to find if we define this function called can split, and it just take the target number. The target number is going to be from the lower bound to high, to upper bound. When we do the function call, it will be false, false, true, true, true. So until we hit 18 here, it will become true, true, true. So that's pretty much how we apply binary search to solve this. The time complexity is just the search space take log and multiplied by n, because for each of those target numbers we want to actually try to do a greedy scan through the array to figure out the number of splits we need to make sure the minimum of all the subarray sums are less than or equal to the target value that we are looking at. Yeah, so it's not equal to, it's less than or equal. So let's code the binary search code. Yeah, that's really the reason that I want to solve this problem, because this problem has a binary search tag. So we're gonna have the lower bound to be the maximum among all those numbers. So we're gonna do is to take the maximum element from nums.begin to the end, and this gives us we want to actually do this to grab the value, and for the upper bound it's the sum of all those numbers, so it's just the accumulator. And a little tricky part is here we have to cast the initial state to be 0 in the long, so that we don't get overflow. Otherwise, if we just put 0, the accumulation would still be in the int type, so it will be overflowing because all the number in some of the test cases are really large. Just initial and mid value there. We got some name conflict. This is called m. So yeah, so that's just gonna be the standard binary search kind of code templates. We're gonna get the middle value, which is this. If you're following my binary search question videos, you get bored by when I type this stuff. We're gonna have a helper function to do this number splits code. Instead of returning this boolean and boolean, I can return this number of splits needed. I think that's a little bit more readable. So just have the function called number of splits with this target value in mind. How many number of splits we need to make sure that the minimum amount all the subarray sums are going to be smaller than or equal to this target value mid. If the split number is larger than the one that we can tolerate, then we want to make sure this target value goes up, so that the number of split that we need can go down. So that's the binary search code. The rest of the stuff is to write a greedy heuristic to enumerate over the array ones to figure out the number of splits we need. So we're gonna have a lambda function here. Lazy, so grabbing everything that I can. We're gonna define this number of splits initially to be 1 because the whole thing itself is 1 split. We're gonna have run a window to accumulate the window sums, subarray sums. Once that subarray sum would exceed the target value by adding that number, we're gonna do a physical split. Bumping up the splitter counter and refresh the window to have that new number as the only element in the window. So just gonna enumerate over the numbers once. So reset, right? So that's the greedy heuristic to determine the number of splits we need to make sure the maximum amount or the minimum amount or the maximum subarray sum has to be sorry, it should be maximum all the way. What was I thinking when I talked through that? Yeah, so this helper function determines the number of splits we need to make sure that all the windows, when we sum up the elements there, the maximum window sum does not exceed the target value. The DP is exhausting, so I kind of lose my focus when I talk about the binary search. Yeah, but this is pretty much the idea. The subroutine here is taking out of n time, and this binary search here we can see it's going to be log of the search space. So it's the sum of stuff, sum of nums subtracted by maximum of numbers. That's the time. So in total, it's these two multiplied together. For space, what do we have? So for space, we have this a single variable, this a single variable, integer variable, and this nothing. This is also just a variable. So this space is constant. Yeah. And if this range is reasonable, it's gonna be if this you know, if sorry, it's log of this. Pretty bad shape. If the log of this is less than m multiplied by n, this is the binary search is gonna be much faster. So let's try this. What? Oh, okay. Wrong? Jeez. Checking. What's the problem? This seems okay. What's the number that I find? Let me just print out this to see. What am I finding? 32. Why is it 32? My upper bound is 32. Why I ended up in the upper bound there? Is this not right? Is it greater than? Yes, it's greater than. If it's greater than m, we have to. If it's a. We're looking at the first target value that can allow us to be less than or equal to m. So in the contrary here, it has to be strictly larger than. Let's try this. This time it's working. So tricky. Alright, so that's the binary search solution. Feels so bad that I got this wrong, even though I solved this early in the morning. In the nighttime, I already forgot about this. Yeah. Anyway, that's the binary search solution to this. Cool.